All right. Hello, everyone. Welcome to a Spotlight 3 session of RMP. So we are delighted to have two amazing talks in our session. The first speaker, Yiding Feng, is going to tell us about his paper on revelation gap for pricing from samples, which is a joint work with Jason Hartline and Yingkai Li. So this talk is going to be followed by a discussion by Yash Kanoria. So the speaker is going to speak for 25 minutes. I'm not going to interrupt the speaker with questions. If you have any questions, please type them in the chat. I'm going to monitor the chat, and then we are going to ask the question from the speaker during the last 5 minutes. And then the discussant, Yash, is going to discuss the paper for 15 minutes. With that, Yiding, the floor is yours, please.
Oh, I want to check. Do I have 25 minutes or 30 minutes?
You have between 25 to 30 minutes, depending on how many questions you get. I'm going to give you some
Cool.
time notification.
Thanks. Yeah. So hello, everyone. I'm Yiding Feng. I'm a postdoc at Microsoft Research. Today, I'll be happy to talk about my joint work with Jason from Northwestern and Yingkai, who graduated from Northwestern this summer and will join Yale as a postdoc. So in this paper, we try to understand the differences between the truthful mechanism and non-truthful mechanism when we are trying to design robust mechanism. And in the first page of my slide, let me give you a very short comparison between the truthful mechanism and non-truthful mechanism. So the truthful mechanism, basically, we are talking about the mechanism where we will ask the agent who participated into the mechanism to review their private preference truthfully. And for example, the second price auction. And the remaining mechanism, which we call the non-truthful mechanism, corresponding to those mechanisms where agents bid in the equilibrium, may not be equivalent to their private preference. And from a practical perspective, so the truthful mechanisms are easier to do the analysis. And that is basically because given the fact that the agent will report truthfully, the mechanism is just a mapping from the true preference to the outcome. On the other side, for the non-truthful mechanism, in order to analyze its performance, usually we need to first characterize what will be the agent strategy in the equilibrium. And another good thing about the truthful mechanism is that we have this seminal results called the revelation principle. And it basically suggests that given an arbitrary non-truthful mechanism, we can construct a truthful mechanism which obtains the same outcome in the equilibrium. And the construction is very simple. We will ask the agent to report their private preference truthfully. And then we will simulate the agent's original strategy in the original equilibrium and output the outcome from that original mechanism. As you can easily to verify that in this construct new mechanism, it's agent's best strategy to report their value truthfully. And therefore, we end up with a truthful mechanism. And because of this revelation principle, in the literature, the majority of the results has been focused on the truthful mechanism design. And on the other side, what we observe is that the non-truthful mechanism is in practice widely used. And here, let me give you two examples. The first one is a sponsor search, where the advertiser will bid for the ad slot on the search engine like Google or Bing. And the auction format used here is a generalized second price auction, which is a non-truthful mechanism. And another example is a Google Ad Manager, which shifts their auction format from the second price auction to the first price auction. And basically what we want to do in this paper is try to give a theoretical justification on the potential advantage to use a non-truthful mechanism. And to do so, the message we will try to deliver is inspired by the following idea from the multi-party computation literature. And here, let me describe this to you. So on a high level, the mechanism design is trying to design mechanism, or let's say protocol, which try to achieve the desired outcome for some strategic agent. And as a computer scientist, I view this as a special case of multi-party computation. Specifically, it will involve different parties, for example, like the mechanism, as well as the agent. And the different party may have their own data, like the agent have their private preference or their private belief about the environment. And the choice between the truthful mechanism and non-truthful mechanism can be interpreted as two different solutions of the following fundamental question in multi-party computation. Specifically, who should be doing what part of computation? And truthful mechanism can be interpreted as a solution which suggests that okay, only the central mechanism should do the computation. It will both incentivize the agent to report truthfully, as well as to achieve the desired outcome. On the other side, the non-truthful mechanism is suggesting that both the agent as well as the central mechanism need to do computation. Specifically, agent need to compute their own equilibrium strategy. And it turns out that this fundamental question has also been answered in the system design community. Specifically, in 40 years ago, when the computer scientists are trying to design the protocol for the computer network, so there is a seminal paper introduced this concept called the end-to-end principle. And the high-level idea is that we need to consider design protocol in a decentralized fashion. In other words, all parties should do computation. And this is kind of coincide with our interpretation of the non-truth mechanism in mechanism design. And it turned out that this seminal framework in computer network enables the protocol which designed 40 years ago continue to succeed nowadays, even though the number of user, application, or the volume of data on the computer network has increased exponentially after 40 years. But the fundamental protocol on the network still remains unchanged. And I think this is quite crazy, right? Because like the hardware or the operation system or the technique in artificial intelligence, they all involve a lot. But on the other side, the protocol we designed for computer network 40 years ago, they are still get success in nowadays. And basically in this paper, they also argue that by focusing on this decentralized fashion, we can end up with simple and robust mechanism. And it will also help us to improve the efficiency. And in this paper, we try to argue that the same type of argument also hold in mechanism design when we are focusing on non-truthful mechanism. And specifically, in this paper, we try to study the so-called prior independent mechanism design framework, which I will formally define in the next few slides. But on a high level, it's basically consider the following scenario, where the seller has no prior information about the type distribution of the agent, but the agent will have the common knowledge about the type distribution. What the seller wants to do is to approximate the Bayesian optimal over the worst distribution. And if you think about this carefully, I will argue that this is very similar to a situation of when computer scientists are designing computer network. Because when they are designing protocol 40 years ago, they may have no idea about what will be the environment nowadays. But for the user or the application, which are actually using the computer network nowadays, they know what is the current environment, and therefore they can do the optimization on their own end to incorporate the current situation, which is kind of like this current situation that the seller does not have the prior information, but the agent do have the common knowledge. And I want to also notify that the classic revolution principle fails in this analysis framework. And this is because revolution principle is basically argue us that we can construct a truthful mechanism by simulate the agent strategy. However, the agent strategy in the equilibrium depending on the knowledge about the prior information. And if the seller doesn't have such information, such kind of simulation is impossible, and therefore the classic revolution principle fails. And because of that, in a previous work, we introduced this concept called the revelation gap, which try to quantify the potential loss to restrict to the truthful mechanism in its prior independent approximation setting. And our results in this paper I will show you is that in a very stylized model, single item, single agent with single sample access, when the seller try to maximize revenue, so there will be a strict loss if we restrict to the truthful mechanism. And the take-away message here is that non-truthful mechanisms are beneficial in pure economic terms. In other words, revenue approximation guarantee when the robustness is desired, specifically the prior independence. And the technical contribution of our paper is that we provide a framework to analyze a non-truthful mechanism by adapting ideas for the classic technique we use for analyzing truthful mechanisms. So far, so good? Cool. So now, I will talk about the model we consider in this paper. So this will be a very simple and stylized model, but we hope that the mechanism we design in this model, as well as the results we establish, can help us to shed insight on the more practical setting. And this model is also considered in the previous literature. So this simple model works as follows. Suppose we want to allocate a single item to a single agent, and we want to do revenue maximization. The agent will have a private value V drawn from some distribution F, and we'll assume that agent knows both of her private value V as well as a distribution F. The mechanism will be a pair of allocation and payment, and it will work as follows. First, it will solicit a bid from the agent, and then the mechanism will observe a sample. And the allocation and payment will basically be a mapping from the pair of bid and sample to the allocation and payment. We will assume that the agent is risk neutral, and therefore from the agent's perspective, her expected allocation given her bid will be taking the expectation over the randomness of the sample, as well as for the payment. And we can define the interim allocation and interim payment to be the mapping from the value to the allocation and payment, assuming that the agent is optimizing their bid using the best response strategy. And we assume that agent's utility is a quasi-linear term, basically her expected allocation times her value minus her expected payment. And because in this work, we try to understand the differences between truthful mechanism and non-truthful mechanism, so we will not impose the incentive compatibility constraint, but still we will impose the individual rational constraint that requires that the agent's utility will be non-negative for all possible value. And we will assume that we'll focus on the objective of the sealer, which is to maximize the revenue, which we will denote it as MF for a given mechanism or a particular distribution. And to help us have a better understanding of this model, let me introduce two simple mechanisms which make sense in this model. The first one, which we call the sample-based pricing, and it works as follows. So the agent will get the item if her bid is above the sample. And if he gets the item, the payment he will make will equal to the sample. And it's easy for you to verify that this is a truthful mechanism. In other words, the agent's best response, the optimal bid the agent can make, will equal to her true value. And we call this a sample bid mechanism because this mechanism is equivalent to posting a take or leave price equals to the sample to the agent. And next, we will introduce another similar mechanism, which we call the sealed envelope. Here, we will restrict the bid space to be binary. So the bid can be either 0 or 1. And the agent will get the item if the bid equals to 1. And the agent will pay the price equals to the sample if her bid is 1. And as you can see, so this is a non-truthful mechanism because the bid space is binary. And the agent's best strategy is to make her bid equals to 1 if her value is greater or equals to the expectation of the sample. And this is easy to see because if he bid 1, so her expected payment will be expectation of the sample. And we call this a sealed envelope pricing because it's equivalent to say that the sealer will set the price equals to S and put it into a sealed envelope and offer this envelope as an offer to the agent. And the agent need to decide to accept it or reject it before say the actual price. Cool. So now let's try to reason about on the sealer side. So first, let's assume that what happens if the sealer knows the type distribution. And if the agent knows the type distribution, we can define the Bayesian optimal mechanism, which will be the mechanism which try to maximize the revenue the agent can get. And by the results from Meyerson, so we know that the Bayesian optimal mechanism is basically posting a single price. And we will revisit this result with more detail in the next few slides. And now let's assume we are in the prior independent setting where the sealer has no information about this distribution. And then we can define the prior independent approximation ratio of a given mechanism M within a class of distribution to be that suppose that there will be an adversary which will pick the worst distribution, which try to maximize the ratio between the revenue we can get from Bayesian optimal, which knows the distribution, versus the revenue we can get from our mechanism. And we will define the optimal prior independent approximation ratio within a class of mechanism by assuming that the mechanism designer will try to optimize the mechanism within this class, which try to optimize this ratio. And now it's safe for us to consider the two possible class of mechanism. The first is a class of truthful mechanism, and the second is a class of all mechanisms which are possibly non-truthful. And we will define the revolution gap to be the ratio of those two quantities. And by definition, this ratio is at least 1. And if it is strictly greater than 1, it kind of suggests that there will be a strict loss with respect to approximation guarantee when we restrict to truthful mechanism. Cool. So now let me introduce a very simple non-truthful mechanism, which attains good pair-independent approximation ratio in this paper. And this is called, we call it sample bit mechanism. And this mechanism will be parameterized by a parameter alpha. And it will proceed as the following 3 steps. First, it will ask the agent to report a bit. And then it will charge the agent alpha times minimum between her bid and the sample. And the agent will get the item if her bid is greater than the sample. And I want to emphasize here that in our mechanism, the agent needs to make this payment regardless of whether he gets the item or not. And it turns out that we are not the first group of people who think about this simple mechanism. It turns out that our sample bit mechanism share very similar format as a BDM method in the experimental economics back to the 1960s. And as a sanity check, you can verify that this mechanism is indeed individual rational because the utility of bidding 0 is non-negative. And then in the next slide, we will see that this mechanism is a non-truthful mechanism because the agent may either overbid or lower or underbid respect to her value. Cool. Now let's try to let me try to show you the approximation guarantee within a class of distribution, which is monotone hazard rate, which is a standard assumption in auction design. So for this part, we start with the following technical lemma, which is trying to show that when the underlying distribution is MHR, the optimal bid for the agent is either bid 0 or infinite. And remember, so the agent will get the item if her bid is above the sample, and he will pay the minimum between her bid and sample times alpha regardless. Therefore, this lemma directly implies that our sample bid mechanism is equivalent to the sealed envelope pricing if the distribution is MHR. And this is because if the agent bid infinite, he will always get that item, and the expected payment he will make is exactly alpha times expectation of the sample. And the proof intuition is also quite simple. We just need to show that the expected utility is convex in the bid. And because of that, the optimal bid will take as a trim point, which is either 0 or infinite. And by reducing our mechanism to this simpler mechanism, sealed envelope pricing, we can show that if the seller has no information about the distribution, but know it is from MHR and has a simple single sample access, he can get a 1.3 approximation with respect to Bayesian optimal, which has a perfect knowledge of the underlying distribution. Cool. So our second result is, let's consider our approximation guarantee for a broader class of distribution, which we call the regular distribution, which I will define in the end of this page. But before that, let me introduce a very simple concept called the Redmi Curve. And it is a useful concept which has been used to understand the optimal mechanism as well as approximately optimal mechanism in this literature. Specifically, let me remind you that the quantile of a distribution basically will be QV will equal to 1 minus FV. And then we can define its inverse function, the value function, to be the mapping from Q to F inverse of 1 minus Q. And the revenue curve will be a mapping from the quantile to the revenue, specifically to map a quantile Q to Q times VQ. And it turned out that this mapping is indeed a bijection. In other words, whenever we are given a revenue curve, it will uniquely pin down a distribution and vice versa. And on the right-hand side, I draw a revenue curve for some distribution. And it turns out that the revenue curve, we can have a very simple geometric interpretation, like, for example, what will be the VQ look like? And for example, given a quantile Q, VQ will be the slope of the straight line going from the origin to through the point of Q, PQ. And as Mayerson showed that the Bayesian optimal mechanism with the knowledge of the distribution F will be posting a single price. And this price will equal to VM, basically will correspond to the quantile, which attains the global maximum on this revenue curve. And we will say our distribution is regular if the corresponding revenue curve is concave. In other words, for you guys who are familiar with the auction theory, it's basically equivalent to say that the virtual value, which is a derivative of the revenue curve, is monotone. Cool. So in the next slide, I will show you a very simple proof on how to use this revenue curve concept to show the approximation guarantee of a simple mechanism. And for our mechanism, and in our paper, we also adapt this idea to show the approximation guarantee for the sample-based pricing, but it will be more involved. And I will highlight the technical difficulty after I show you this simple proof for a simple mechanism. Specifically, let's consider a simple mechanism that we will just set the take a leaflet price equals to the sample. And here I will show you a very simple proof to show that this will help us to attain an approximation guarantee of 2 when the class of distribution is regular. And we will show this by considering its revenue curve. And remember, so the regular distribution means that this corresponding revenue curve will be concave. And we will start this proof by first write down the revenue we can get from this revenue curve. And this, by definition, this is that we will sample a distribution, we will sample S from a distribution, and the probability that we will sell is 1 minus FS. And we can write down this term in the quantile space. This is equivalent to say that we will sample a quantile uniformly at random, and the revenue we will get will be PQ. And you can immediately say that this quantity is equivalent to the area below the revenue curve. And similarly, we can write down the Bayesian optimal revenue, which is equal to the PQM, where QM is a quantile which hits the peak of this revenue curve, which is equal to the area of this green rectangle. And therefore, we can use the following idea, which we call the revenue curve reduction, which basically we try to start with an arbitrary revenue curve, and we will adjust it to a new revenue curve corresponding to a distribution F star, such that we will preserve the Bayesian optimal revenue, but we will, on the other side, we will minimize the revenue from posting the sample. And to do this, basically, we will end up with a revenue curve which will have this triangle shape. As you can verify, to preserve the Bayesian optimal revenue, which basically requires that the 2 revenue curve need to have the same peak. And it is indeed the case for this triangle revenue curve. And to minimize the revenue of price posting, as we suggest, the revenue of price posting is the area below the revenue curve. And because we require the revenue curve to be concave, so the worst case is this triangle. And now we can reason it. So basically, we have end up with a new revenue curve, which is a triangle revenue curve, and we can analyze its approximation ratio by elementary geometry that the area of a rectangle and triangle with the same width and height, the ratio will be 2. And that's finished the proof. So basically, in summarize, so basically here we use the idea of trying to start with an arbitrary distribution, in other words, a revenue curve, and convert it to a new distribution and its corresponding revenue curve, which preserves the Bayesian optimal revenue, but minimize the revenue from our mechanism. And
so you have 5 minutes left.
Thanks. And now we want to impose this idea to our sample-bit mechanism in order to identify the worst distribution. And the technical challenge here is that when we are trying to adapt this approach to non-truthful mechanism, by adjusting the revenue curve, it will also affect the equilibrium behavior of the agent. In other words, agent's bidding strategy will also change. And to overcome this issue, we provide the following characterization of the bidding strategy in our mechanism, which basically will be 2 monotonicity characterization. And using those 2 characterizations, we are able to adapt this revenue curve reduction approach such that we will still preserve the Bayesian optimal revenue, but we will try to minimize the equilibrium bid and the corresponding payment for every quantile. And in the end of the day, we are able to show that within the class of regular distribution, the prior-independent approximation ratio of our sample bid mechanism is upper bounded by 1.84. And before I finish my talk for the non-truthful mechanism, let me discuss one final question: is that can non-truthful mechanism achieve Bayesian optimal revenue? And just to give you some literature review, so if we have multiple agents, so for a non-truthful mechanism, it is possible that we can achieve Bayesian optimal by considering the mechanism designed from the implementation theory. Basically, those mechanisms behave as follows. They will ask the agent to report their prior, and they will tell the agent that I will shoot you guys if the prior you report to me are not the same. And because the agents have a common prior, so it will be an equilibrium strategy for them to report their prior truthfully. And because of that, then the agent can safely run the Bayesian optimal mechanism. And personally, I consider this type of results is suggesting that in this multi-agent setting, this crazy result suggests that we are giving the mechanism designer too much freedom, which enables such kind of crazy mechanism and crazy results. However, in our setting, we can show that this is not the case. Specifically, it's impossible for us to design a non-truth mechanism which to achieve the Bayesian optimal. And the intuition is to focus on the class of uniform distribution, which I will not talk about the detail here. But in the end, so we are able to show that regardless of how complicated your mechanisms are, even if you allow the mechanism to have multiple communication between the theory and agent, the approximation ratio you can get is at least 1.07. Cool. Finally, let's talk about the behavior of the performance of the truthful mechanism within this model. So this is basically solved by a very beautiful paper by Aloy and Besbes in 2019. Basically, they consider the class of sample-based pricing. And in this paper, we show a minor lemma which shows that every prior-independent truthful mechanism is equivalent to a sample-based pricing. And because of that, we can directly obtain the approximation guarantee for the truthful mechanism in this model. And put all the numbers together. Basically, the Aloy and Besbes paper, they characterize the optimal approximation you can get among the truthful mechanism. And in this paper, we identify a very simple mechanism, sample bit mechanism, which attains the approximation ratio better than the optimal approximation we can get from the truthful mechanism. But unlike the results they established in the truth mechanism, you can see that the upper bound and lower bound are very close to each other because the non-truth mechanisms are hard to analyze. So in our results, there is still a huge gap between the upper bound and lower bound. And putting up numbers together, basically, we show that there is a revolution gap. So in this stylized model. And it turns out that this kind of revolution gap not only exists in this model when we try to maximize revenue, it also exists for welfare maximization when we consider IID agents with public budget. And this is shown by our previous work. And the good mechanism, the good non-truth mechanism there is the all-pay auction, where all agents will report a bid, and the agent with the highest bid gets item, but all agents will pay their bid. As you can see, this shares some similarity of our sample bid mechanism that agent will pay regardless of whether he gets item or not. And this different trade, this relation gap also exists, and it's actually infinite in the bilateral trade setting where there is a seller and buyer who both have private information. And a good non-truth mechanism there is a random offer mechanism. And here, let me just to repeat the takeaway message in this paper is that when we are the non-truth mechanism is beneficial when we are consider approximation, when we require robustness. And usually the mechanism we end up with in this framework will also be quite simple. And that's all for my talk. So you can check our paper for more detail. And any comments, feedback, or questions are super welcome. I'd be happy to reach out through my email, as well as to talk to you here in the gather. That's all. Thank you.
Thank you, Yiding. Let's thank the speaker. We have time maybe for one question. There was no question in the chat. If there is no question from the audience, I'm going to ask one. All right. So, Yiding, my question is there easy intuition behind why MHR is going to help the sealed envelope pricing to be a good non-truthful mechanism in terms of revenue approximation?
Yeah, so basically, I think interpretation here is that. So one interpretation is that. So when I talk about truthful mechanism, so the agent actually does not need to. So when we try to implement the truthful mechanism, the agent just need to report their value truthfully. In other words, they do not need to rely on their own knowledge about the underlying distribution, the distribution of the sample. But when we are talking about sample-based mechanism, like when it is MHR, basically we are posting a price equal to the expectation of the sample. That is kind of like, even though Seller does not have the distribution knowledge, but he can utilize or he can beneficial from the fact that the agent has such kind of information. And with respect to MHR distribution, this is extremely helpful because we know that the expectation of the sample has is greater or equals to, so its quantile is greater or equals to 1 minus, so it's greater or equals to 1 over E. And therefore we can guarantee that it will be at least a E approximation if we post the price equals to the expectation of the sample. And by optimizing this ratio alpha there, we can actually boost the revenue a little bit more.
Excellent.
And that's it.
Thank you. Thank you. It was a great answer. So in the interest of time, let's move to the discussion. So Yash, the floor is yours.
Thank you. Do you see my screen? And does the screen look okay?
It does.
Okay. Well, thank you to the organizers for their work and for the invitation. And thanks to Yiding for that great talk. So I am going to keep it brief, and I'm going to pose a few questions, and hopefully Yiding or Jason or Yingkai can give some answers to these questions or just their thoughts. So quick summary, I mean, Yiding has given a very good talk. So this was about single item, single agent auctions with a single sample access, and they were looking for a robust mechanism that does well even without knowing the prior of the agent. The question was that is a truthful mechanism sufficient to get the best possible approximation ratio? And in short, the paper proves that the answer is no. It actually gives a concrete and very simple non-truthful mechanism that beats the best truthful mechanism. And this is the sample bid mechanism. Okay? So just a quick reminder, the sample bid mechanism says, give me your bid. I have access to one sample. I'll take the minimum between the two. I'll multiply by this tuning parameter alpha, and that's going to be how much I charge you. And you have to pay me whether or not you get the item. And you'll get the item only if your bid exceeds the sample. Okay, so I think this is extremely simple and potentially could be practical, or maybe it's already implemented in practice in some form. So this is one question, right? Is this used in practice, or do you think there is practical potential in some context? I will just keep going, finish my thing, and then hand over back to Yiding. So a couple of strengths of this work. So one is that this sample bid mechanism is extremely simple and practical, and much more so than some of the previous prior free mechanisms that have been proposed. Which I mean, this is a little bit harsh on them, but it's sort of roughly asking the agents to provide their joint prior over all the valuation distributions, shoot agents if they disagree on what they report, and then run the Bayesian optimal mechanism. Okay, so this requires at least 2 agents and requires a strong knowledge assumption on the agents, and is demanding of them in terms of what they need to communicate to the mechanism. Another strength is this new technical tool, which is that they are using this revenue curve reduction for the first. I'm not sure if it's the first time, but they're using this in a non-traditional way, which is to analyze a non-truthful mechanism. So this is very exciting, and one question is where else can this technique be useful? So one potential concern, which also Yiding had touched on in his talk, is that, you know what, you can have a sort of a different kind of revelation principle, which would apply even in this prior free setting. And this would require agents to report not just their valuation, but also their prior beliefs to the seller, who can then simulate the equilibrium strategies and actually have a truthful mechanism in this way. Now, this I think is not a major concern because this kind of approach is impractical for a few reasons. So once again, it seems unreasonable to ask agents to report their prior beliefs. This would require a very complex kind of reporting. Even the knowledge assumption is very strong in this type of a mechanism. And even analyzing the mechanism is hard. The mechanism itself will be complex, and these are not appealing from a practical standpoint. Okay, and this is perhaps why we do see non-truthful mechanisms in practice in multiple contexts. Think of the first price auction or generalized second price auction. This work is advancing now. There's a few papers out there. One was by Yiding and Jason. So there's a few sort of settings in which we now know that you can actually get a better approximation factor with a non-truthful mechanism than the best you can get with a truthful mechanism. So this will be, I think this is my last question. Is there something more general that we can now try to move towards in terms of understanding when are non-truthful or non-revelation mechanisms going to be better than the best you can get with a truthful mechanism? That's it from me. So the floor is yours again, Yiding.
Thanks, Yash.
Yes, thanks. Yeah, thanks, Yash. I think all are pretty good question. So, so I think so. Basically, so for the first question, is this mechanism used in practice? So then the honest answer is I'm not sure. So I think so. So first, as I mentioned, so our mechanism. So the mechanism we try to design shares very similar format as the BDM method in the experimental economics. And basically they try to design those experiments to understand the willingness to pay for the agent. But I didn't follow up their literature to see that if actually is actually later implemented in practice or not. And another thing I want to mention is that, so this idea of that the seller does not have the distribution knowledge, but only have a single sample access. I think this can be also interpreted as the current literature on this kind of data-driven mechanism design. And it's basically, you can interpret a sample as suppose we have the original data point from the previous transaction. Okay. And so I think, so maybe immediate a step for our work is to say that if we can come up with, we can get some data and to do some counterfactual analysis about whether the revenue guarantee from our mechanism in the actual data, and I think that would be cool. Yeah.
Thank you.
And so we are also quite excited about trying to use this idea of the revenue curve reduction in this non-truthful mechanism. And initially, when we try to analyze to study this problem, so there is a huge difficulty that the bound of the truthful the optimal prime dimensional approximation ratio for the truthful mechanism is so good. For example, for the MHR distribution, it's roughly 1.5, and for the regular distribution is roughly 1.9. And for most of the results for the non-truthful mechanism, like price of energy, usually you will end up with a bound like 1 minus 1 over E, or let's say half approximation, which all of them are not sufficient for us to beat. So the ratio Aloha and Besbes established for the truthful mechanism. Therefore, this requires us to have a fine-grained analysis for this type for the non-truthful mechanism. And therefore, what we end up with is to adapt this kind of revenue curve reduction technique, which I actually used for analyzing a truthful mechanism, and usually they can use to identify the optimal competitive ratio. And we adopted here, but the difficulty, as I mentioned, is that when we try to modify the Redmi curve, the bidding strategy will also change. And we get success in our paper because that our mechanism is so simple. And because of that, so we are able to characterize how the bidding strategy will change when we do the modification. And I think, so this type of technique may also be helpful when we are considering some other stylized model, for example, single item, two agent, and we want to do revenue maximization in a prime balance setting, and we are considering non-truthful mechanism. I think in such space, it may be useful. It might be helpful that we can use this kind of revenue curve reduction to identify non-truthful mechanism.
Thank you.
Awesome.
The last question.
So we have time for more questions.
No, meaning I had one more question, but it's fine to also skip it and go to the audience question. Yeah. So Yiding, the question was, can there be a more general theory of
Yes.
Yeah.
So I would say that, so I think there are, so I actually it's very excited to see that maybe in recent 2 or 3 years, so there are some very amazing papers which study this difference between truthful mechanism and non-truthful mechanism. Let me give you 2 examples. So basically there is a paper by Babayev et al., which they comparing the difference between truthful mechanism and non-truthful mechanism with respect to the computational complexity and also communication complexity. And for example, you can consider a setting where we are trying to do a combinatorial auction. So for example, we have multiple items and the agents utility of the item are, for example, submodular. And there, so we can consider, so can we design the polynomial time mechanism which approximates the which try to approximate the optimal welfare. We require the mechanism itself to be polynomial time computable, but initially the results also requires that the agent need to have the so there will be a gap between the approximation you can get when you are assuming that agent has infinite computational power or also need to be polynomial time computable. And specifically, if agent can only compute the result in polynomial time, so you can show that there will be a gap between the truthful mechanism and non-truthful mechanism. And there will be a similar type of gap established for the communication complexity. And I think trying to answer those questions from the computation or from a complexity perspective is also quite interesting. Yeah.
Thank you so much.
Excellent. I actually have one more question for you, Yiding. Oh, Santiago, please go ahead.
Yeah, so one question. Great paper. Again, I'm very excited to see how you can compare truthful and non-truthful mechanisms. So when you think about non-truthful mechanism, then the message space could be arbitrarily large. And then you discussed this briefly. Now, in your mechanism, it's very simple message space. You know, you're just reporting a bid. So what are your thoughts about like kind of more complex message space? Do you think that if you go more complex, then perhaps you can attain better performance? Or you think that like the optimal mechanism within this non-truthful class is going to have like a message space that is as simple as yours?
Yes, I think that's a good question. So I think it is possible. So I'm saying it is possible that there indeed exists a more complicated mechanism with a more complicated message space which have a better approximation guarantee. But my personal and you can apply the revolution principle to assume that the agent will report their prior as well as their private type, and you can write the incentive compatibility constraint there. So that will, so you can write down a very infinite dimensional optimization program, which will exactly captures so the the class of non-truthful mechanism. But my concern is that, so when you have such a rich space, I think so the high chance is that it's impossible to do the optimization. And I think it will be extremely hard to identify the optimal one within this class.
All right.
So yeah.
So in the, please.
Thank you.
I guess in the interest of time, I would like to move to the second talk. Thanks everyone for the great questions and thanks for the great discussion, Yash. Let's thank the speaker and the discussant again. All right, so we are delighted to have our second speaker, Jerry Anunrojwong. I hope I pronounced your last name correctly, Jerry. So he's going to tell us about on the robustness of second price auctions in prior independent mechanism design, which is a joint work with Santiago, Balseiro, and Omar Besbes. So the talk is going to be followed by a discussion by Jason Hartline. With that, the floor is yours, Jerry.
All right, thanks. Hello, everyone. I am Jerry Anunrojwong, a PhD student at Columbia Business School. Today, I would like to present my work on the robustness of second price auctions in prior independent mechanism design, joined with Santiago Balseiro and Omar Besbes. To motivate this problem, suppose we have an item and n potential buyers, but you don't know their willingness to pay. What do? There are many possible ways we can sell this item. We can post a price and sell it to anyone who is willing to pay that price. We can run a second price auction where each bidder submits a bid, the highest bidder wins and pays the second highest bid. We can run a second price auction with reserve, where the highest bidder wins and pays the maximum of the second highest bid and the reserve price can be deterministic or random. We can run a first price auction, where the highest bidder wins and pays her bid. We can run an all-pay auction, where the highest bidder wins and everyone pays her own bid. And we can think of many more ways to sell an item. The mechanism design perspective systematically considers all possible ways to design the rules of the game, that is, the mechanism, and find the one that best achieves an objective. Here is to maximize revenue, while taking into account buyers' incentives. Our focus in this work is on robust mechanism design. Why robust mechanism design? The classical mechanism design theory assumes that the seller knows the environment perfectly and designs the mechanism with that in mind. In particular, it assumes a known common prior. Often, it also makes strong assumptions on agent behavior, that agents are Bayesian and will play the Bayes-Nash equilibrium. The theory is elegant, but the resulting mechanism often depends very intricately on details about the common prior distribution and how bidders behave strategically, details which are often not available in practice. We therefore want to develop a detail-free mechanism. There are two fundamental questions. What is an optimal detail-free mechanism? And how much can we expect to perform without details relative to the best we could do? This work is the first to give prescription for an arbitrary number of buyers across a wide spectrum of distribution classes, which capture different dependent structure between agent valuations, from arbitrary dependence to independence, and the intermediate regimes. We now formulate the problem more formally. We want to sell one indivisible good to n buyers. Note here that the number of buyers is arbitrary. This is in contrast to much of the previous work that dealt only with 2 buyers because 2 buyers were easier to deal with. We will optimize over what we call direct mechanisms. A direct mechanism is specified by an allocation rule X and a payment rule P, such that each bidder I submits her valuation VI truthfully, so the valuation vector is V. And bidder I is allocated with probability XIV and pays PIV, which are functions of everyone's report. The mechanism is subject to dominant strategy, incentive compatibility, and individual rationality constraints. These incentive constraints mean that each bidder prefers to report her true value and to participate in the mechanism in the first place. The dominant strategy part means that these IC and IR constraints hold for every valuation. This means that we do not need to assume that bidders are Bayesian or know anything about other agents in order to be truthful, which is a form of robustness against misspecification of bidder behavior. Now we focus on the distribution class F. We want the mechanism to perform well against any distribution in a given class. The objective is worst case over all such distributions. Throughout, we will assume that the upper bound on the support is known. Without loss of generality, this upper bound can be normalized to be 1. We will consider different distribution classes which capture a spectrum of dependency structures between bidder valuations from arbitrary joint distributions to IID. This Venn diagram shows you the distribution classes we consider, which capture a spectrum of dependence between bidder valuations. On the one end is arbitrary joint distributions, where the dependence can be completely general. On the other end is IID, where each bidder is independent and identically distributed. We can constrain the arbitrary joint distributions more and require that agents are exchangeable, which means that agents are in some sense symmetric and can be permuted. It turns out this restriction still gives the same power as arbitrary distributions, and the worst case distribution in this class effectively has only one active random bidder, so bidder valuations are negatively dependent. But we find that most distributions in practice are positively dependent, so we want to study classes that extend IID to capture positive dependence. One such class is mixture of IID. Another such class is exchangeable and affiliated. We will discuss more what these terms mean in the next slide. As we have already said, exchangeable means that agents are symmetric and can be permuted. Affiliation is a standard notion for positive dependence in classical auction theory and mechanism design. Roughly, affiliation means that a high value of one bidder's estimate makes high values of the other's estimates more likely. While affiliation is commonly studied in Bayesian settings, we are the first to study it in robust settings. Lastly, mixtures of IID are commonly used in statistics and modeling. We can interpret it as having a hidden random type, and valuations are IID conditional on this type. We can also show that mixtures of IID implies non-negative correlation between agent valuations, which further supports this class as capturing positive dependence. Now we focus on the objective in the problem formulation. Our objective is the regret on revenue, which is the difference between the benchmark revenue and the mechanism revenue. As we discussed before, we evaluate the performance of a particular mechanism by the worst case regret, the highest possible regret over all possible distributions in a given class. Note here that we focus on the regret because the benchmark gives a natural scaling on how well we can expect to perform, and the gap between the ideal performance and the actual performance is an interpretable quantity. In contrast, to maximize worst-case revenue, we need additional constraints, such as known mean, because otherwise the worst case is simply that everyone's value is 0, so the revenue is 0 and we cannot do any better. Here, we take the benchmark to be the maximum possible achievable revenue when the valuation is known, that is, the highest valuation out of n valuations. We can also interpret this benchmark as the social welfare benchmark, since this is the maximum achievable welfare that is achievable by any efficient mechanism, that is, a mechanism that always allocates to the highest bidder. We now put all the ingredients of the problem formulation together, which means that we can write the problem mathematically using a minimax formulation as follows. Given a distribution class F, the seller moves first and chooses a mechanism. Nature then moves second and chooses a distribution F from a given class, such that the seller wants to minimize the regret and nature wants to maximize the regret. The regret is the expectation under F of the difference between the benchmark and the revenue. The mechanism is prior independent, meaning that the mechanism doesn't need to know F and doesn't depend on F, and has a performance guarantee over all F in a given class. So it is detail-free in the sense that it is not fine-tuned to the knowledge of F, and is robust to this lack of distributional knowledge. As discussed before, we will only consider dominant strategy, IC, and IR mechanisms. So each buyer always reports the true valuation and doesn't need to know other buyers' distributions. This is another aspect of robustness on bidder behavior. Our main contributions are summarized in this diagram. The second price auction with random reserve is minimax optimal across many distribution classes. For the class of IID distributions, exchangeable and affiliated distributions, and mixture of IID distributions. These three classes that capture positive dependence all have the same minimax optimal mechanism and performance, which depends on N. While for the class of exchangeable distributions and arbitrary joint distributions, these two classes that capture general dependence also have the same minimax optimal mechanism and performance, the same as N equals 1 case. As we can see in the slide, the main theorem first states the structural result that under these distribution classes that capture positive dependence, the minimax regret problem admits as an optimal mechanism a second price auction with random reserve supported from some R star to 1. Furthermore, we can also characterize the CDF of the reserve distribution in closed form. We can also calculate the R star, which is the lower bound of the support of the reserve CDF, as well as the minimax regret value explicitly as well. This means that our result is not just an existence result. While we prove that the problem admits the second price auction with random reserve as the minimax optimal mechanism, we can also characterize the mechanism explicitly as well, which allows us to make quantitative statements regarding the mechanism and the value of competition, and so on. Our work is related to several strands of literature. There is a long line of literature on classical mechanism design pioneered by Meyerson, but we depart from that by relaxing the common prior assumption. The closest body of work to us considers the minimax regret when the distribution can be arbitrary with bounded support by Birchman and Schlag, Aaron and Maglaras, Caldente et al., and Kokijit et al. Some other works consider IID bidder assumption, but they can only deal with 1 or 2 bidders. Some other works maximize the revenue rather than minimize regret, or consider other forms of robustness to information structure and higher order beliefs. There are also a significant stream of literature on approximation ratio results for many buyers, as outlined in these surveys. But these works focus more on proving bounds in more complex settings rather than deriving exactly optimal mechanisms. There are no exact optimality results in the literature that deals with an arbitrary number of IID or affiliated buyers, and this is the focus of our work. The challenges of our problem is that the space of all mechanisms is large, the space of all bounded distributions is large, and most importantly, the problem is non-convex due to class restrictions such as IID. This makes our problem different from most other works in most previous other work. We believe that apart from the results themselves, our methodology that we came up with to handle this challenging class of problem is also of independent interest, and is potentially useful for other minimax problems as well. Our approach is via a saddle point argument. Let RMF be the regret under mechanism M and distribution F. If the saddle inequalities hold, then M star is an optimal mechanism and F star is a worst case distribution. This M star F star is such that fixing M star, the optimal F is F star, as you can see in the red, and fixing F star, the optimal M is M star, as you can see in the blue. Intuitively, this is true because we can view a minimax problem as a zero-sum game between the seller and nature, and the condition describes the Nash equilibrium, where both players are best responding. The seller chooses a mechanism to minimize regret, and nature chooses a distribution to maximize regret. We then apply necessary conditions to pin down M star and F star in a principled manner. This diagram outlines how we pin down M star and F star with necessary conditions. First, we have the RMF, regret under mechanism M and distribution F, assuming IID. We then conjecture that the optimal M is an SPA with reserve phi. So we can write R phi F, the regret under reserve CDF phi, and distribution F, which can be written in two ways, using integration by part. The first expression is regret phi, which is linear in phi. The second expression is regret F, which is a separable function of F. We first look at regret phi. The saddle condition means that phi star is optimal over all phi, given the optimal F star. Because the regret is linear in phi, this means that the coefficient of every phi term in the regret must be 0. This gives an ODE for F star, which pins down F star. Now we consider regret F. The saddle condition means that F star is optimal over all F given phi star. Because the regret is a separable function of F, optimizing over all F can be done pointwise. We can then take the first order condition and set it to 0, which gives us an ODE with phi star and F star. But we have already determined F star, so this gives an ODE from phi star, which allows us to determine phi star, the optimal reserve CDF. We can look at the structure of the optimal mechanism, the reserve CDF. Previous work by Bergman and Schlag only solves the one bidder case. Our work is a significant generalization of Bergman and Schlag, when we can characterize the optimal reserve CDF of n IID bidders for every n. We see that it is supported from some lower bound R star onward to 1 and as expected. Furthermore, as n increases, the reserve distribution decreases in a first order stochastic dominant sense. But even with infinitely many bidders, we still have positive reserve price with probability 1. The problem doesn't become degenerate. We can also compare the minimax regret under the optimal mechanism with two natural benchmarks. Without any information, the first natural mechanism to try is SPA0, second price auction without reserve. We would like to emphasize that even computing the minimax regret and the worst case distribution for this mechanism is non-trivial, and we can only do it because our paper proposed a broadly applicable framework. For each value of n, we can compute the minimax regret for that n, as shown in this first row. The next level of refinement is to add a fixed deterministic reserve price. We can characterize the minimax regret of SPA R with fixed reserve R for any R. So we can compute the minimax regret under optimal R star, as shown in the second row. Lastly, we compare these two benchmarks to the performance of an optimal mechanism opt, which we have already shown to be a second price with a random reserve. We can see from this table that the optimal mechanism gives a significant improvement relative to two natural benchmarks. The minimax regrets are lower. While we have been talking mostly about NIID bidders so far, we would like to emphasize again that the exact same result also holds for the class of mixtures of IID and exchangeable and affiliated distributions as well, as shown in this diagram that we have seen before. In order to prove the results in the class of exchangeable and affiliated distributions, we need a new technical innovation, where we prove novel bounds comparing order statistics that are applicable for distributions in this class. Lastly, our results allow us to quantify the value of competition in a minimax regret framework. As you can see in this plot, for the class of IID, exchangeable and affiliated, and mixture of IID, minimax regret is decreasing in n, and it converges to a positive number as the number of bidder grows large. This means that with positive dependence, competition has some value, but there also is an unavoidable gap between the ideal and the actual performance. In contrast, for the general dependence classes of all and exchangeable distributions, the minimax regret is always 1 over E, and competition has no effect. We can also identify the worst case distributions F in the IID case for each n, as shown in this picture. So far, we have solved the case of 0-1 or 0B support. We can also solve the case of AB support with n buyers and all the 5 distribution classes as well. Here, we know both the lower bound A and the upper bound B of the support, and we can characterize minimax optimal mechanisms as follows. For A over B low, the same second price auction with random reserve is still optimal. For A over B high, a variant of second price auction is optimal. But instead of discarding the item with some probability, that is, when it is below the reserve, as is done in the second price auction, instead, in our mechanism, we allocate the item randomly to everyone else but the highest bidder. And for the intermediate regimes, some form of interpolation between these two mechanisms is optimal. Apart from the regret objective, we can also compute the approximation ratio objective, defined as the ratio between the revenue and the benchmark. This ratio objective can be converted to a variant of regret through the epigraph formulation. And we need the AB support results for this. The original result with support 0B is not enough because the worst case ratio is 0 in that case, when we only know the upper bound of the support. To conclude, in this work, we undertake a systematic study of prior independent mechanism design. We give a closed form characterization of a minimax optimal mechanism, knowing only the upper and the lower bounds of the support. Our methods apply in a general framework with n agents and many distribution classes, IID, mixtures of IID, exchangeable and affiliated, exchangeable and arbitrary joint distributions. Our results show the strength or lack thereof of different distributional class assumptions and quantify the value of competition. There are many avenues for future work. We can pose this problem with different support assumptions, different benchmarks, and different notions of robustness. Also, here we assume we do not know anything except the class membership of the distribution, and we can ask what the form of additional information about the distribution might look like and the value of that information. That's all. Thank you for listening, and I welcome questions.
Thanks, Jerry, for the excellent talk. We didn't have any questions. Let's thank the speaker first. So we don't have any questions in the chat. So people should feel free to unmute themselves and ask questions if they have. I have a couple of questions.
All right, should I stop sharing my screen or should I continue?
No, I mean, I'm gonna ask my question as you're sharing. So have you thought about non-truthful mechanisms to kind of connect what you did to the previous talk? Like if you look at the space of non-truthful mechanisms, do you think there is a characterization for the min-max optimal, either in terms of regret or approximation ratio?
We do not consider non-truthful mechanisms in this work, and we believe that the techniques would be substantially different. I mean, here we in fact impose a very strong truthful assumption, which is that we only consider dominant strategy, IC and IR, because we do not want to assume anything about how agents behave. And this is like
Right.
in contrast to like, it is a different philosophy from like, if you assume non-truthful mechanism, then you also have to assume that agents play some sort of equilibrium. So I would say that they are, yeah, they are like quite different from this
I
work.
guess one other thing about my question is if you allow any kind of communication between the seller and the buyers, then because of implementation theory, basically you can implement the optimal mechanism. Maybe the question is not even completely well defined in the space of non-truthful mechanisms. I'm curious to see what Jason thinks about this. All right. Any other questions from the audience?
Are there questions in the chat?
There was a question. Actually, there was a discussion. Let me relate that to you. Maybe it's intrigues an idea. So there was a question that what would happen if you don't know n, because your assumption is you know n. Jason thinks that a lower bound on n would suffice, meaning that if you run the mechanism with this conservative lower bound on n, then it's going to work for a larger n. What do you think?
I think it is possible. I have to check more carefully on that. I mean, if it is true, then we can say that like the limiting mechanism with like infinite n would work, and that would be nice. Because we
That's
know
the
that
opposite. It's the
is just-
lower end mechanisms
wait.
work for higher n, but not the
Oh,
other way around. So
oh wait, yeah.
the n equals 1 mechanism will work for all n, but it gets a worse bound as well.
Oh, yeah. So I think our framework allows us to like to compute the minimax regret of like pretty much like any class of any form of mechanism with this type. So I think that it should be possible to like compute what the worst case regret would look like if you use a mechanism for like a different n to like to the setting. And that's a very good question.
But I guess it's also a, sort of conceptual question about whether the mechanism can be a function of n or not. Because usually you got some bids and you do whatever you want, and checking to see how many bids there are is a pretty easy operation. But in looking for mechanisms that are robust to the number n, are you trying to also be robust against spam bids and that kind of thing? Because then you would maybe worry about that.
Yeah.
I think it's a cool question.
Yeah, very good question. Good food for thought.
I have one quick technical question. So,
sorry.
Yeah, Yifan, please go ahead. Shoot your question. I'm gonna ask.
Yeah, okay, thank you. I just have a quick question about the min-max form. You mentioned that this problem is going to be non-convex and non-concave. Can you better illustrate like the structural information about the min-max optimization and what key generic structure you use to design the roadmap to get the optimal Nash equilibrium point?
Yeah, so when we say that it is non-convex, we are looking at this.
Before guessing, right? After guessing, it is not.
Yeah, so so you see here that like the expectation is like it is going to be linear in the joint distributions F. So like when you are looking at like the class of all distributions as has been done before, it is linear. But like once you assume that it is IID, like this like joint F would like decompose into like products of marginals, which means that it is no longer convex. So you cannot use tools. You cannot directly use tools from like linear program and its infinite dimensional variance on it. But we can still use the idea of saddle point argument, where like if you come up with like a one-dimensional class of mechanisms that we conjecture is optimal, then like you can use like first order conditions to pin down what those what those mechanisms should look like. And this is essentially an even shorter summary of like our roadmap here.
Just a follow-up clarifying question, Jerry. So what you're saying, if you after you guess that you're searching over the class of second price auctions with random reserve, then things are going to be convex, concave, actually linear with respect to the two distributions.
Well, they're not linear, but they are. But well, I guess I mean like
Right.
well, I guess like they are separable. Which is like actually like non-trivial in that like you can write down the regret purely in terms of the CDF.
Right.
Which means that you can do like you can do like point-wise optimization on those. Kind of like how like in like the standard Myosin problem you get like a separable like function.
All right. Excellent. So in the interest of time, let's actually move to the discussion. Jason, the floor is yours.
All right. While I'm getting my screen share set up, thanks a lot for the invitation to talk about this paper. It's one that I'd seen on paper lists, and I'm super excited to have the opportunity to look into it in more detail. Cool. So just to summarize, the main result is that the second price auction with a random reserve has min-max optimal regret for single item revenue maximization. There are a couple of details about this. The solution is via solving for the solution of the zero-sum game between nature and the mechanism solving exactly for it. In the case where you restrict to distributions that are have some kind of independence, then the bound improves with n, and in the limit we get about 0.28 regret. And in the correlated case, the worst case is when n equals 1, and then the regret is 1 over e. I really, again, I was looking forward to reading this paper, and it was not disappointing. I like the analysis, and it's a great result. And at the, I'm going to have some discussion of sort of some framing and how to think about these kinds of results. But then I think there's some really interesting open questions that this kind of analysis is going to let us do. And so I want to sort of talk about those. So first off, I want to just there's a whole host of frameworks that people look at when they are considering robust mechanism design or optimization in other contexts. And there's, absolute max-min optimization when you want to find the mechanism that maximizes the worst case over environments of some performance benchmark. There's the min-max ratio when you're looking for the mechanism that has the smallest ratio of the optimal performance for the environment to the mechanism. Again, so here opt is always better than the mechanism, and so we want this ratio to be small. And then there's the min-max regret, which looks at a similar quantity but an additive difference instead of a ratio. And okay, so let's talk about these different frameworks a little bit. All of them are popular, and I think when you have a bunch of frameworks for doing robustness and all of them are popular, it's good to understand when and why. And I'll tell you just off the bat, I'm a little bit biased that I like ratios, and one of the reasons why is that if you look at the absolute regret, you see it's sort of going to be most pressing probably at the small end and this is what Jerry said, is when if you had an unlimited range, right, the worst regret is when everything's zero. Sorry, the worst absolute robust ness is going to be zero. And so, if the small end is very small, then you're going to be really focused on when things are horrible, and maybe giving up on performance when actually performance could be quite good. And so you end up with no constraint on mechanisms, things are quite good. And so that's sort of a challenge for the absolute framework. And similarly, when you look at, just skipping over to the right-hand column, when you look at regret, it's the same, you look at the same difference sort of everywhere. And as you might imagine, when the stakes get higher, it's, can be harder to do well to the same extent that you could do when stakes are small. And so probably this is going to be focusing attention really at the high end. And if you look at the mechanisms Jerry was describing, they really were having a significant probability of posting really high reserve prices because they're really focused on this high end. So we do see that outcome. The ratio, on the other hand, one of the reasons why I like it is because I really like, statements about mechanisms that scale, meaning they work at any scale. So I like families of environments that are closed under scalings. And if you like families of environments that are closed under scalings, then if I take the all environments and I sort them by the performance of opt, then the ratio where it's going to be tight everywhere. And so it really focuses attention at all scales. And that's one of the reasons why I like it a lot. And you can make statements that don't have assumptions on your environment, like, this mechanism is a good mechanism because it does this, right? And you don't need to say anything about what the scale of the question was, which I quite like. Now, of course, as I said, these are used all over the place. And so there are, really outstanding papers in all of these columns. I did put asterisks on some of the papers in the regret column because they're usually when I write, the optimal mechanism in an environment, and the reason I wrote opt sub e of e is because this is the optimal mechanism for the environment that we're in, for the objective we're in. And that's not really what this paper was looking at. Is looking at the welfare as the benchmark, not the optimal revenue as a benchmark. So it's a little bit different, but I think it's intellectually in this camp. So I'll put it there. And so a question of when are these different frameworks good? I think the absolute framework is a good framework when the set of environments we care about is very restricted. And so some of the settings where this has been used are, for example, Carroll's paper, where the distributions of marginals are known across different dimensions of the problem, but the correlation structure is not known. And so that for that very restricted family of environments, you could see, an absolute notion of regret being an interesting notion. Again, I said I like the ratio notion when the environments are closed under scalings. And this additive notion of regret is a good notion when there's an absolute scale that the problem is being defined on. And so you're not looking at all possible scales. Another setting where I really like absolute regret is when in the limit with the number of agents that essentially regret is vanishing. Now, that's not what's happening in the present paper, but it is what's happening in this other paper, the Kleinberg-Layton paper on online learning, where as the number of rounds you get to play the online learning algorithm increases, your regret vanishes. And so that's one setting where I think additive regret is a very good notion. Okay, so problems with scale, so let's talk about it a little bit. So the paper assumed that value is between 0 and h is known. And once you assume something like that, you might as well normalize it so h is 1. But just to see how this comes in, let's let h be a variable for a second. And so the solution they gave is the second price auction with a random reserve. That reserve distribution depends on the highest bid. And the regret they give is linear in this highest bid. And one point is that the distribution that is optimal actually does place lots of mass at very high bids. Okay, and so if you were to try to apply this theory, you have to think very carefully now about what you think the upper bound on the range of bids is. Because if you try to be conservative, I mean, so actually is being conservative choosing a low upper bound or a high upper bound. Actually, the conservative thing is to choose a low upper bound and be wrong about it. Because if you guess wrong and there are actually bids that are higher than your upper bound, you still get some revenue. Whereas this mechanism will start, posting random reserve prices that are, above any of the bidders' values that you see if you choose H2 big. And one thing I like to think of as an exercise is just think about what if you got H wrong by a factor of 2. You just lost twice your revenue, half your revenue by doing that in this model. And so I'm a little bit nervous about that. That is, if you got H wrong too high by a factor of 2, then you lost half your revenue. And I'm a little bit nervous about that. And I just want to reference a line of literature that also had this issue come up. So actually, an old paper of mine looking at online pricing ended up getting a regret that was something is in fact just a little bit super linear, depending on H, the range of values. And then a really nice paper said that actually you don't have to suffer this this linear cost in the range of values. So like if you conservatively estimate an H that's too big, you don't suffer because of it. And they actually showed that you can get regret proportional to what is the optimal price to post, which of course, you need to have H at least the optimal price to post, otherwise you're going to be very wrong. And the only dependence on H is this log term, which in logs, if I, go twice as high or 10 times as high, it's not a big deal. So I really like this analysis. I thought that, did a good job dealing with this issue of scale. Cool. So as I said, when is this absolute notion of regret a really nice notion? It's really nice when the scale is sort of there's an obvious scale that's factual and you can't maybe get wrong. And so that's why I think a killer app for this paper might be procurement, i.e. reverse auctions instead of forward auctions. Okay, and the nice thing about reverse auctions is scale is absolute. The auctioneer is a buyer now with value V. The sellers the bidders are sellers with costs. Look, so the buyer is trying to procure this good at a cheap cost, and the most they could, the best thing that they could do is if it was 0, the cost is 0, right? Then they would get V, and so the scale of the problem is sort of obviously V, right? That's the best they could get in this problem, and this really sort of defines an absolute scale where you want to be optimizing. And so I actually think this is the killer app for this paper. I didn't do the math carefully, but I'm pretty sure that a corollary of the results of this paper is that the min-max regret for procurement, the second price auction with the random reserve is optimal. And I believe the math the paper already tells you exactly what the solution is to this problem. Okay, so I think the paper solved this killer app where there really is an absolute scale and gets this nice result. Cool. So I promised you at the beginning that I was really excited by some open questions that I think are hinted at the analysis of this paper. And so let's just get into that. So if there's one agent, this paper, and actually the prior papers, show that the regret is a 1/E factor. And in fact, there's a line of literature in what's called the price of anarchy of auctions that essentially uses this theorem of that's in Bergman and Schlag and this paper to generalize beyond single item environments to really complex environments and show essentially that And now this is changing the objective completely, that the welfare in any equilibrium is going to be a good approximation to the optimal welfare. Okay, so this generalized to basically show in winner pays bid matching markets, the regret essentially of the optimal welfare of society is most of 1 over E factor of the optimal regret. It's a sort of an additive regret of 1 over E. And this generalizes to complex marketplaces like winner pays bid matching markets, crazy environments. Okay, and the proof is basically the analysis of this paper plus analysis of complex mechanisms, and it somewhat decomposes. And the decomposition is in this paper that I had with Daryl Hoy and Sam Taggart. And so this analysis from the welfare and equilibrium, this is again for this correlation structure where the worst case is with n equals 1 agent, essentially, as this paper showed. And if you restrict to independent distributions, then these analyses of equilibria actually show that things like the first price auction with independent agents actually has better worst case equilibria than the first price auction with correlated agents, which is kind of like what this paper was, the present paper was showing as well. And so, really new result actually by Liu and Jin is that this this relative regret is 1 over E squared with independent agents. Okay, and so the thing that I'm really excited about actually is, because this paper gives us improved analyses of something like the first price, something like best response in a first price auction for independent distributions. Could that analysis be used to give general price of anarchy results for really complex mechanisms that improve on the 1 over E approximation factor that we get from the Serganes-Tardosh result that allows correlation? So the question is, with independent distributions in very general settings, can we improve on these worst case bounds we get with correlation? With that, I really like this paper again. Very succinct and technical analysis that gave a nice, easy to interpret conclusion.
Awesome. Thanks a lot, Jason, for the intriguing discussion. We are short in time, so if there is any question, I would suggest taking it offline. Let's thank the speaker and the discussants again. All right. So we're gonna continue with a short networking break for 30 minutes. Now we have a little bit less than that, and then we'll continue with the regular sessions after. All right, see you guys around.
Hey, Jason, thanks for the discussion. It was great.
Oh yeah, thanks. I mean, it was a really interesting paper.
It's no, I like the slide 3 especially. I mean, indeed, with all the different objectives and what's a different way. I was actually at the conference 2 weeks ago with Ben Brooks, where